Welcome to springlib.
For the function f of x is equal to x to the 1 over x, we want to graph the function, explain the shape of the graph by commuting the limit as x approaches 0 from the right or x approaches infinity. We want to estimate the maximum and minimum values using our graph and then use calculus to find them exactly. And lastly, we want to use the graph of our second derivative to estimate the x-coordinate of our inflection point. So over here on the left, I went ahead and graphed the function with two different viewing windows. So the first one helps us find what our maximum and our minimum should be. And so it looks like our maximum value occurs around 2.718. And the output for that is about 1.4447. So at least when we try to calculate this exactly, this looks really close. Let me actually do this in a different color. 2.718 is approximately the value for E. So if we do this correct, then we would think when we actually do part C, finding this exactly, our value for X should be about E. All right. So that gives us our local max. So our max. And over here at 0, 0, that gives us our minimum. Now, the reason why I had these two different viewing windows is because in part B, we want to explain the behavior for each of those limits. So on the right of 0, we want to show that it's actually going to approach 0. And as x approaches infinity, if we look at this second graph here, it looks like it's getting really close to y is equal to 1. So we would expect that y is equal to 1 is a horizontal asymptote. All right, so let's actually see if we get those same results. So if we were to just plug this in directly, we would get, well, x approaches 0 from the right, it's just 0, and 1 over 0 is infinity, and that's an undeterminate form. So we don't know what that means, or at least I surely don't know what that means. So we need to rewrite it into a form that we do know. So a nice trick we can do is to introduce the natural log and e. So e to the, so if I take the natural log of that, it's going to be natural log of x over x now. And if we were to go ahead and apply the limit, remember we can move it inside using the chain rule for limits. So this could be the limit as x approaches 0 from the right of natural log of x over x. And remember, we can only do that since we know e to the x is a continuous function. All right, so we have that. Now, natural log of x, if I approach from 0 from the right, that goes to negative infinity. And if I approach x from the right, that's going to go to 0. And since these values are going to be positive, if I'm dividing into negative infinity, and I keep getting closer and closer to 0, that's going to go to negative infinity still. It's just going to go a lot faster. So this should be e to the negative infinity, which is 0. So the behavior as x approaches 0 from the right checks out. Now let's check for this other behavior. So if we do infinity first, it's just going to be infinity to the 0. And once again, that's an indeterminate form. I don't know what that's supposed to mean. So let's go ahead and rewrite this using the same little trick that we did before. And I'm pretty much just going to skip to this step right here. So we should be able to rewrite this as e to the limit as x approaches infinity of natural log of x over x. Now, if we were to just apply this directly, we're going to have e to the infinity over infinity. And so again, I don't know what that's supposed to mean, but this implies that we can apply L'Hopital's rule. So by L'Hopital's, this will be equal to, so e, the limit as x approaches infinity, of So we take the derivative of the numerator and the denominator. So the derivative of natural log is going to be 1 over x. The derivative of x is just going to be 1. And so we can rewrite that as e to the limit as x approaches infinity of 1 over x. And we know 1 over x approaches 0 as x goes to infinity. So that's going to be e to the 0 or just 1. So our end behaviors for both end up checking out. Right. Now, to finish off part C, so we estimated what our max and min should be. Now we want to find them exactly. And so remember, to do that, we need to take the derivative and find our critical values. And before we actually do that, I'm going to rewrite this to make it a little bit easier for us to take the derivative. And I'm going to write this as e to the natural log of x over x, just like what we had before. All right, now, if we wanted to take the first derivative, so first derivative, we're going to need to use chain rule. So chain rule says take the derivative of our outside function, which is e. Well, that doesn't change anything, so it's just going to be e to the natural log of x over x. But then we need to take the derivative with respect to x of natural log of x over x. And to take the derivative of this function, we're going to need to use chain rule, or quotient rule, I'm sorry. And now, one thing I'm just going to do is rewrite this again, just as x to the 1 over x, just so I don't need to keep on writing that e. And then let's go ahead and use quotient rule to take that derivative there. So remember, quotient rule says we're going to take what we have in the denominator, so low d high, the derivative of natural log of x is going to be 1 over x, and then minus high d low. So this should be natural log of x times the derivative of what we have in the denominator, which is just 1, all over what we have in the denominator squared. All right, so now we can go ahead and just use a little bit of algebra to rewrite this as x to the 1 over x. And 1 minus natural log of x over x squared. Now what we want to do is set this here equal to 0. And so we already know that this part here will only equal 0 if x is equal to 0, but since here in the denominator we can't have it equal to 0, we would only set 1 minus natural log of x equal to 0, and then we just need to solve for x. So let me go ahead and zoom out a little bit. So we're going to add natural log of x over, get 1 is equal to the natural log of x, exponentiate on each side, and we're going to get e to the first power is equal to x, which is just e. Now we can go ahead and plug this into f of x. So f of e is going to be e to the 1 over e. And so this here is going to be our actual value for our max. All right. And in part D, we need to know what the second derivative is going to be. So let's just go ahead and find the second derivative since we're here. So if I want to take the derivative of this, what we're going to do is, so d by, actually, let me go ahead and just write this out again. So d by dx of x to the 1 over x times 1 minus natural log of x over x squared. Now, to take this, we're going to use both the product rule and the quotient rule. So I'll go ahead and do it in this order. So 1 minus natural log of x over x squared times the derivative with respect to x of x to the 1 over x plus them in the opposite order, so x to the 1 over x times the derivative with respect to x of 1 minus natural log of x over x squared. So we already found this derivative in our last part, so let's go ahead and write that down. So that should just be x to the 1 over x times 1 minus natural log of x all over x squared. And taking the derivative of 1 minus natural log of x over x squared, we're going to need to use quotient rule. So remember it says low, so x squared, d high, so the derivative of what we have in the numerator here, derivative of 1 is 0, derivative of negative natural log of x is going to be negative 1 over x. And then minus, then the opposite order, so 1 minus natural log of x times the derivative of x squared, which is 2x. And then all over what we have in the denominator squared. So before it was x squared, now it's going to be x to the 4th. And once you do a little bit of algebra, this here will actually simplify to what I have here for our second derivative. All right. Now, after we did this, I went ahead and graphed the function. And since we just want to estimate where these points of inflection are, we should end up with, so this, let me use a different color actually. So we have this point here and this point here. And so the value for each of those, so the first one is about 0.58, so 0.582. And this other one, I went ahead and zoomed in a little bit closer just to make sure that we actually do have a change in concavity. Because remember, we want it to go from positive, negative to positive. And that value there, we end up with about 4.368. So 4.368. And remember, we just want to check that there is a change from concave up to concave down or down to up. And so to the right of our first value, it is concave up because f double prime of x is strictly larger than 0. And to the left is going to be concave down. So that is a point of inflection. And our other one is concave down to the left, concave up to the right. So we have our other point of inflection.